Hello, thank you for joining me. My name is Sandy Wagner with CreationScienceEssentials.com. My mission is to share the truth of biblical creation. Knowing the basics of science can help you better understand evolutionary and creation models. I made this video to teach you what you need to know about scientific models. Models can be extremely valuable when used properly. However, when they are misused, they can lead to false results. Evolutionary thinking has led to issues that underlie so much of our modern cultural and policy issues. Did you know that climate change, eugenics, gender ideology, and sanctity of life issues are the result of an evolutionary worldview? Much of the justification for policy decisions that are outside of God's plan for us arise from scientific models that assume the universe is billions of years old. Could this assumption lead to wrong conclusions? My goal for this video is to explain the strengths and weaknesses of models to help you look critically at the findings resulting from scientific model conclusions. I've had many years of experience working with models, including performing probabilistic risk assessment in the nuclear industry and using engineering models at NASA. I'll share some of the things that I've learned along the way. Let's get started. Here's what you'll learn in this video. We'll begin looking at mathematical models. Then we'll move to engineering models and how they can be used to optimize designs, improve reliability, and increase efficiency. With that knowledge, we'll move into scientific models, where we'll look at the scientific method and the difference between observational models and forensic models. Finally, we'll look at what questions to ask. We'll look at what are the assumptions and what is a confidence interval. We'll also explore logical fallacies that might be used in the conclusions. And then we'll look at whether or not hypotheses are testable and falsifiable. The first thing you need to know is that science and engineering are largely described by mathematical equations. Most of the models produced today are computerized. This is because computers can perform calculations with amazing speed. As scientific models have become more complex, the need for speed has caused growth of sophisticated computer models to explode. Whenever scientists develop their models, they make many assumptions, including the state of variables when their model is initiated. Those assumptions can significantly change the resulting output of the model. Let's study a simple example. Imagine you go to a friend's house for dinner. When you arrive, you notice a burning candle. You might wonder when the candle was lit. To answer that question, we'll create a model where it is expressed as an equation. To find the time the candle was lit, you first need to find the amount the candle has burned down. To find how many inches the candle has burned, you subtract the height of the candle when you arrived from the height of the candle when your friend lit it. Then you'll find how many hours the candle has been burning by dividing that number by the burn rate in inches per hour. To find the time the candle was lit, you subtract the amount of time the candle has been burning from the time you arrived. We'll need some missing information before we can solve this equation. The first piece of data is easy. You can look at your watch. Let's say you arrived at your friend's house at 6:30 p.m. Next, you need to determine what was the original height of the candle. Let's do a little research. You log on to Amazon and search for the candle. You find one that looks the same. It is 9 inches tall, so you assume that your friend's candle was 9 inches. You also make a note that the specifications say that the burn rate is 1/4 inch per hour. So you'll assume the original height was 9 inches and the burn rate is 1/4 inches. What was the height of the candle when you arrived at your friend's house? You have a pretty good eye for measurements and estimate the height at around 7.5 inches. Now you plug in the numbers into the equation and conclude that the candle had been burning for about 6 hours. That means your friend lit the candle at 12:30 p.m. After dinner, while you gather to watch a movie, you say, "I've determined that you lit that candle at 12:30 p.m. His wife, looking confused, says, "No, I lit the candle just before you arrived." Where did we go wrong? Let's look a little deeper. We need to start with our assumptions. Were they valid? Remember we found a candle on Amazon and assumed it was the same candle? Other candles on Amazon were 8 and 10 inches. Perhaps we chose the wrong height. Even if our assumption that the 9-inch candle was correct when it was bought, we also assumed that the candle had not been burned before. It's quite possible that the candle was burned previously, so when the candle was lit today, the initial height of the candle would have been less than our assumed 9 inches. Models use something called initial conditions. The candle height when it was lit is an example of an initial condition. When we know the value of the conditions, our values will be more accurate than when we have to make a guess. Whenever we are looking at something that happened in the past and we are not there to measure it, you have to make assumptions. In this case, the type of science that we are doing is called speculative, historic, or forensic science. In other words, we depend on assumptions that we cannot test. It is important to remember that a model's result is only as good as its assumptions. Our assumptions also did not consider environmental changes before we arrived. Perhaps your friend opened the windows or turned on a fan. The wind would have caused the candle to burn more quickly. We assume the burn rate is constant, but factors such as environmental changes likely would lead to errors in your model. The point here is that when you're reading about scientific results, you should always ask the questions, who was there to observe the phenomenon? And did the scientist make assumptions that he could not observe? If the answers are no to one observes the phenomenon or he made assumptions he could not observe, then the model is speculative. Now let's turn our attention to engineering models. Excellent examples of mathematical models are found in engineering and design. Let's jump into this world and see what we can learn about highly tested models with lots of strong data. Engineering models are used to simulate how well a design will perform in the real world. The best ones use large amounts of historical performance data on the components used in the design. Component data includes things like failure rates, mean time to failure, and failure causes. They also include performance data. When components are operating in various environmental conditions, such as high and low temperatures, high and low pressures, and high vibration. That is because these conditions cause wear and tear, so it's very important to know how they will affect the product in the field. Industries such as nuclear power plants, aircraft, and refineries are ideal for engineering models because they have many years of operating data and failure rates of components are well known. Because engineering models have grown in complexity and need huge amounts of data, many commercial computer-aided design, or CAD packages, have been created to analyze designs. These packages allow an engineer to create a model of their system and the process it will operate in. They contain a component database with the capability to choose and modify the components in the system. They also allow the engineer to change operating parameters in order to select among various design choices. These models sometimes use sophisticated statistical analysis, such as Monte Carlo methods, to simulate a large possible number of outcomes. Monte Carlo simulation is a computational technique that uses repeated random sampling to model uncertainty and estimate the probability of different outcomes in complex systems. These methods are ideal for high-risk industries where accidents can result in catastrophic consequences, such as nuclear power and human spaceflight. Models can be used to optimize design. For example, let's say NASA plans to add a module to the International Space Station, the ISS. Engineers will use models to ensure that temperature in the module is warm enough to prevent water from condensing on the walls. Water in a spacecraft is a serious safety concern. The engineers determine that ISS airflow must be sufficient to keep the module's walls warm enough to prevent condensation. So they develop a CAD model to test various airflows. The result helps them to establish design and operational requirements for airflow into the module. The result is an optimized design that increases crew and equipment safety while minimizing power and cargo requirements. CAD models are often used to improve reliability. This is extremely important for high-risk industries such as nuclear power and aircraft, spacecraft, and fossil fuel production. These models include a part failure database and an interface to model the design. The model then runs various scenarios using different parts and configurations. Engineers can then select the most reliable design. Often, designers will perform probabilistic risk assessment to further improve reliability of their systems and to minimize operational risk. Models are also used to increase efficiency. For example, engineers use wind tunnels in automotive design to improve fuel efficiency. They were first built to test aircraft performance, then they were used to test spacecraft. Realizing this could be a great tool to evaluate efficiency, the automobile industry started testing cars in wind tunnels. As fuel efficiency standards became stricter, these models became invaluable. Aerodynamic models include databases containing large amounts of wind tunnel data. They provide a user interface to build and modify virtual models of the car's design. Engineers can then modify the design and find the most efficient one to take to production. Once they complete their analysis, they may build a physical model and test it in a wind tunnel to verify their results. These computerized models are very sophisticated. They include complex thermodynamic models that simulate airflow across the vehicle. As a matter of fact, they've become so sophisticated that sometimes they can even eliminate the need to test their designs in physical wind tunnels. Now that you've learned about some great engineering models, you should have an idea of how they simulate engineering designs. Let's move into the world of scientific models and apply what you've learned so far to learn about the world of scientific models. But first, let's review the scientific method. Understanding the basics of scientific study will help us to better understand models that scientists use to advance knowledge. I like to say that science is not a noun. That's because science is a verb. It is the process by which scientists gain knowledge. Here's the process. A scientist observes some physical phenomenon. Then he develops a hypothesis or guess to explain the phenomenon. Next, he creates an experiment to test the hypothesis. If it fails the test, the scientist throws out the hypothesis and looks for another. If the test doesn't fail, he continues to test his hypothesis. For example, Isaac Newton studied moving objects and developed hypotheses to explain different types of movements. He also invented calculus, the mathematics that describes his hypotheses. They have been repeatedly tested so successfully that they are now considered to be scientific fundamental natural laws. His laws have been used for hundreds of years for all kinds of inventions, including the rockets and spacecraft that took men to the moon. By the way, did you know that Isaac Newton was a devout Christian? As a matter of fact, he wrote more about the Bible than he did about math and physics. Here's an example of scientific knowledge obtained by successfully testing a hypothesis by observation. Newton's laws of motion were applied to planetary motion when astronomers discovered that planets perturb the orbits of neighboring planets. Astronomers noticed that Uranus's orbit was perturbed and hypothesized that an unknown planet was causing that perturbation. Later, two astronomers, John Gall and Enrique d'Arrest, observed Neptune using a telescope. In this case, observation validated scientific models. On the other hand, today many areas of science, such as climate change and evolution, deal with phenomena that cannot be tested or observed. Since they cannot be observed, they are speculative, and the scientific method cannot be strictly applied. Therefore, forensic science is an alternative that may be used to study these areas. Forensic techniques can be used to study things that happened in the past. This type of science uses unobservable assumptions because no one was there to observe or measure them. Much of this study is simulated using computer models, while some, such as criminal science, analyze evidence in sophisticated laboratories. You may have seen forensic science techniques in television series such as Matlock, 2020, and CSI. Here is an example how forensic science is used in our legal process. Let's say someone committed a murder. There were no witnesses. Police arrive at the scene and collect evidence. After studying the evidence, they develop a theory of the case. Their theory points the detectives toward additional evidence to be collected. Once they have a suspect, and if the sufficient evidence indicates their guilt, they refer their case to the district attorney. He assembles a grand jury to determine if there is sufficient evidence to indict the suspect. If the grand jury indicts, the case goes to a jury trial. At the end of the trial, the jury returns a verdict. The suspect is deemed guilty or not guilty. Notice the innocent is not an option for the verdict. That is because you can never prove a person did not commit the crime. The lawyers can only convince the jury that there is or is not enough evidence of guilt, beyond the shadow of a doubt, to convict the person. Although observational and forensic science are different, you can draw an analogy with the scientific method. You can never prove a hypothesis is true. You can only disprove it. When you are presented with a scientific conclusion, there are some questions that you can ask to determine if it is valid. What are the assumptions? What are the initial conditions? Were they observed or were assumptions used? What rates are assumed? How were they determined? Are there any factors that could change those rates that were not considered? For example, climate change models assume only carbon-based gases in the atmosphere cause global warming. They do not include solar flare activity, volcanic eruptions, and water vapor content in the models. In reality, these factors are more responsible for the Earth's temperatures than are carbon-based gases. Some of these scientists claim that carbon is a pollutant. Unfortunately, they do not appear to understand that carbon is essential to life on Earth. Plants breathe carbon dioxide and exhale oxygen. We need to breathe. So the point here is to look for assumptions and think critically about them. All data the engineering models use comes with a margin of error. That is important because you need to understand how much confidence you can have in the resulting model output. Component failure data are readily available in industry databases. They have been established by testing huge numbers of components over decades. However, they all have uncertainty because components fail at various points in their life cycle. Let's say you are designing an aircraft landing gear and use a component failure rate in the model. You look it up and it has a failure rate of 5 years plus or minus 0.5 years. That means the component is expected to last between 4.5 and 5.5 years. This range represents what is called the confidence interval. An important factor in determining uncertainty is sample size. The greater the sample size, the more confidence you can have in the failure rate value. Let's look at an example to see how sample size can impact analysis in a scientific study. Let's say we want to determine how much radioactive material has been released into the environment from a nuclear materials processing plant. This simplified example describes an actual experience, although in reality, the analysis is much more complex. It does, however, give you an idea of how confidence intervals factor into an analysis. A manager at the plant sends a technician into the field to determine how much plutonium is in a lake near the plant. When plutonium decays, it emits alpha particles. Alpha particles are essentially helium nuclei. So you want to count how many alpha particles are emitted from a sample. You have an instrument that detects the particles that are emitted and displays the results. He takes a sample and puts it into his counting instrument. He sets it to count the number of particles detected at 1-minute intervals for 10 separate counts. So the total time is 10 minutes. When the counting is finished, he takes the average of the counts. The average number is 10 counts per minute. However, there is a wide variation in how many counts the detector registers for each minute. The number of alpha particles the instrument counted ranges from 1 to 19 for each 1-minute interval. The reason for this large variation is that radioactive materials do not decay at a constant rate, so the uncertainty for each 1-minute count is quite large. The technician records the number of counts per minute is 10 plus or minus 9. This result has a very large confidence interval. The number of counts per minute could be 1 or it could be 19. The smaller number looks great. However, the larger number might be greater than environmental regulations allow. Obviously, your answer is not acceptable. By the way, the manager's next action is to assign an engineer to determine how to reduce that confidence interval associated with counting these low-level samples. Increasing the number of count times from 10 to 100 would reduce the confidence interval. I hope this example might help you to better understand why you should not just accept a number printed in a news report without knowing the confidence around the number. For example, when you read that radiometric analysis says that the Earth is 4.6 billion years old, you should ask, what is the confidence interval? If you can find the answer, you will be surprised. Critical thinking can help you find problems with scientific results. Scientists sometimes use logical fallacies in defending their evolutionary theories. These fallacies undermine rational discourse by distracting us from core issues and lead us to false conclusions. Here are a few examples to look for. Ad hominem. This is attacking the person making the argument instead of addressing the argument itself. For example, all scientists believe in evolution. You can't trust Dr. Peters. He's not a real scientist because he believes in creation. Straw man. Misrepresenting an opponent's argument to make it easier to attack. For example, people who think that global warming is not true support polluting the environment. False dilemma. Presenting only two options when more exists. For example, if we say the Bible is true, we'll have to throw out all technological advancement. Hasty generalization. Drawing a broad conclusion from insufficient evidence. For example, I met two scientists who believe the Earth cannot sustain the current population, so we need to sterilize everyone so people cannot have babies. Circular reasoning. Using the conclusion as a premise to support itself. For example, this fossil is 60 million years old because it was found in this rock. This rock is 60 million years old because this fossil was found in the rock. Appeal to authority. Arguing something is true because an expert or authority says so without evidence. For example, we should believe in extraterrestrial life because NASA scientists believe there is. In order to test scientific hypotheses, they must be testable and falsifiable. For example, biological evolution claims that life evolved from non-life millions of years ago. Since no one was there to observe whether or not this happened, there is no way to test or falsify this claim. Remember that you learned about forensic science earlier? Those tools might be used for studying things that happened in the past, but theories based on these hypotheses cannot rise to the level of observational science. The bottom line, a good scientist is skeptical. Learn to ask the right questions before blindly accepting conclusions of scientific study results. In conclusion, here are the important points to consider when you hear about conclusions based on scientific models. Put on your skeptic glasses when learning scientific model conclusions. Don't be intimidated by experts. Don't blindly accept conclusions from scientific models. Asking the right questions may bring to light fatal flaws in the theories. Asking the right questions and answers may convince you that the model is right on track. Finally, let biblical truth be your guide. Ask yourself, does this result contradict Scripture? If so, look deeper. The Apostle Paul told us that we perceive the truth by his invisible attributes. We have no excuse for substituting God's word with man's word. Do you want to learn more about this topic? Visit the Science by 6 page at creationscienceessentials.com. There you will find videos on some of the topics we discussed in this video. Thank you for joining me to learn about scientific models. If you enjoyed this video, please give me a like, subscribe to this channel, and send me a comment. You can also scan the QR code on the screen to go to my website. You can sign up for my newsletters so you'll know when I publish new videos. While you're there, you can find lots of great free videos from well-respected creation scientists in the searchable Creation Resource Catalog. Hope to see you again soon. Thank you.